Hello, today we're going to talk about structure 2.1.1 and 2.1.2. This is all about ionic compounds, how they're formed and their properties. So let's just talk about some general things with ionic structure. Typically you're going to have metal and a nonmetal. Let's use X for nonmetals actually instead of N. And what's going to happen is the metal is going to transfer an electron to the nonmetal. So you'll be left with a positively charged metal, a negatively charged nonmetal, and then they attract each other because of those opposite charges. And you wind up with this structure that is alternating between positive and negative ions. The metals are positive and the nonmetals are negative, like this. And it's going to, have a slightly different structure depending on the formula of your ionic compound, but the positive charges will always be canceled out by the negative charges, and you will always have this repeating structure that forms a lattice. All right, let's talk about cations and anions. Cations are formed when atoms lose electrons, and it's usually a metal. Anions form when atoms gain electrons, and they're typically nonmetals. I say typically because hydrogen is kind of weird, and hydrogen can act as either a metal or a nonmetal. Hydrogen could gain or lose electrons. But for the most part, we're going to follow this pattern. Now, the reason for this is because metals tend to have fewer valence electrons. So let's take something like lithium. Lithium has 3 total electrons, and I'm going to use a Bohr model just because it's quick and easy to draw and quick and easy to see which electrons are the valence electrons. Now, in reality, we know that the Bohr model is not an accurate model. We know that the electrons are actually doing this 1s2, 2s2, where the core electrons are in a 1s spherical orbital and the valence electrons are in the 2s spherical orbital. So in this case, but we can see that there's one valence electron, one electron in the outermost energy level. And because there's only one, it becomes relatively easy for it to lose that one electron and turn into a lithium +1 ion. And that lithium +1 ion would have a Bohr model with just the 2 core electrons now, and its electron configuration would just be 1s2. And the same thing is true when you have some slightly larger atoms. Let's look at another one. Excuse me. So let's say we've got something like magnesium. Magnesium has 12 electrons total. And again, I'm going to use a Bohr model for simplicity, but effectively you're going to have 2 in the first energy level, 8 in the second energy level, and 2 in the outermost valence shell. Its electron configuration will be 1s2, 2s2, 2p6, 3s2. So these electrons are all core electrons. There's only 2 that are valence electrons, so it's pretty easy for it to lose those 2 and become a magnesium with a +2 charge. Excuse me. Now, so that's for your positive ions, for your cations. Let's talk about anions. So let's choose something like, let's do fluorine. Fluorine has 9 total electrons. So it has 2 in the first level and 7 valence electrons. So its electron configuration would be 1s2, 2s2, 2p5. And so it has 7 valence electrons. It's very close to having a full energy level. So this is our outermost energy level. It's 1 away from filling up that p sublevel. And so it's more likely for fluorine to gain an electron and become 2p6, and you'd have F with a -1 charge. And so that's what happens with anions, where it's easier for it to gain electrons to fill up a level. And then, so there is a shortcut to figuring out the charges using the periodic table. This is my very simplified drawing. excuse me, the group 1 metals have a +1 charge, and we should do this properly. So a 1+ charge, 2+ charge for group 2. Group 13 has a 3+ charge. Group 14, starting with carbon, they don't tend to form ions, or not very often. You'd have to use context clues of the situation to see if it did form an ion, but it doesn't typically. So then group 15, where you have nitrogen starting off, it's a 3 negative charge. The next one over is a 2 negative charge, and the next one over is a 1 negative charge. And then noble gases don't want to form any charges typically because they already have a full shell. They already have full energy levels, so it's not likely for it to gain or lose any electrons, so it's not going to form a cation or an anion. So again, 1 + 2 + 3 +, skip over, 3 - 2 - 1 - is 0. And so that's your pattern for finding for those representative elements. Now let's talk about transition metals. All right, so there's a periodic table again. So we already said that the group 1, group 2, group 13, 15, 16, 17, 18. So it's very easy to tell. Transition metals are in the D block, and they can have variable oxidation states, which is a fancy way of saying it can have different charges. And I know oxidation numbers and charges are different, but for the purpose of this lecture, we can say that transition metals just can change charge. So like copper, for example, can form copper with a +1 charge, and it can form copper with a 2+ charge. 2 different charges of transition metal. Now, the reason for this is because the transition metals have electrons in a D sublevel now. So like as soon as you get to the transition metals, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1 would be like the first one. So the 4s and the 3d are very, very close in energy. So it's not as simple as saying, well, it just loses the whole outermost. That's not really true, because the 3d, and some people will write this in an opposite order, but because they're so close in energy, it could lose the d electrons, it could lose the 4s electrons, it could lose both. So because of that D sublevel being so close in energy to 4s, it can form those different charges. So we're going to have to indicate somehow in our name the charge on the transition metal when we're naming these compounds, or we can use context clues of like how many of a certain ion it's bound to figure out the charge. Okay, so let's relate this to Coulomb's law. There's a couple things going on here. In order for a cation to lose an electron, or rather an atom to lose an electron to form a cation, the attraction between the protons in the nucleus and the electrons has to be broken for the electron to be able to leave. So there's a couple different factors that make that easier or harder. The more protons you have, so the number of protons or the nuclear charge, can affect it, and as well as the atomic radius. So what that boils down to is the quantity of charge, and then the distance. And those are always the two factors for Coulomb's law. So the more protons, the greater the charge, the more it is attracted. The protons are pulling on the electrons more, and so that it will take more energy to remove it. And we call that energy the ionization energy. Distance works in the reverse. The further away it is, the easier it is for that electron to leave, the smaller the ionization energy. For anions, we want to talk about gaining electrons to form an anion. So we're still having protons attracting the electrons, but we're basically pulling an electron in from the outside so that it is now part of the atom. But the same things affect it. The number of protons. More protons is going to pull on the electrons more. And then smaller radius, shorter distance, means that those protons are going to have an easier time of pulling the electrons in. So all of that is for Coulomb's law. And this we can talk about in terms of electron affinity. So both of those things are affecting how well an atom is going to form a cation or an anion. It also affects the atomic structure, the lattice structure when you're forming an ionic compound. So once you have a cation and an anion, they are going to attract each other because of those opposite charges. We call those electrostatic attractions, although some people will say Coulombic attractions, because it's the opposite charges are attracting each other. And the strength of that attraction is affected by the same two things, the quantity of charge and the distance, or the radius. So the larger the charge is, like if you have a metal with a 2+ charge, that's going to attract better than a metal with a 1+ charge. Now, if you have different size ions, the smaller radius ones will have a better attraction because their nuclei can get closer together. Like they can physically get closer to each other. So smaller radius or larger charge will increase the attractions between cations and anions. All right, so let's review how to name ionic compounds. When you have a simple ionic compound like, let's do something like this, BaCl2. If the metal is a representative element, so not a transition metal, you just need to write the name of the metal, barium in this case. And then the nonmetal, the ending changes to "ide." So instead of chlorine, it's chloride. Let's try another one. If we have something like, let's do like CaNO3 too. Calcium is not a transition metal. NO3 is a polyatomic ion. Polyatomic ions have their own names. NO3, the name is nitrate, so it's just calcium nitrate. Now, the number does not affect the name in this case. So if you have something like AlCl3, you would have aluminum chloride. So even though they have different numbers, that's kind of assumed as part of the name because we know barium and aluminum form different charges. They're inherently going to have different number of chloride atoms. You should also know how to name using transition metals. So if I have something like Fe2O3, or let's just do 5FeO. Those are two separate compounds. Because transition metals can have different charges, they can form different compounds. And so we need to indicate that in the name. You will have to figure out the charge on the transition metal for that situation and use that charge in the name. So oxygen always forms -2 ions. And because there are 3 of them in this compound, that's a -6 total. And so the irons have to add up to +6. And in this case, each iron would have a 3+ charge. In our other compound, there's only 1 oxygen and 1 iron. So the iron here is a +2 charge to balance out the oxygen evenly. And so in their names, this first one would be iron 3, Roman numeral 3, oxide. You still change the ending of the nonmetal to "ide, but the Roman numeral 3 tells us that it has a +3 charge on the iron. Our other compound here is iron 2 oxide because the charge on the iron is 2. Now, I like to talk about charge for this because it's pretty straightforward to figure out. Fortunately, the charge happens to be the same as the oxidation state for these transition metals. Oxidation state is not exactly the same thing as charge, but for metals, it winds up being the same number most of the time. So you'll see a lot of times people will say the transition metal compounds are named using their oxidation state, which is effectively the same thing for this purpose. Just a quick note about ionic compounds and their formula units. So formula unit is just a way that we can say that it's a ratio of the ions in a compound. So let's look at two examples. If I have something like sodium chloride, and that's a simple one, or if I have something like aluminum oxide. The sodium is a group 1 metal, so it tends to form +1 charges. And chlorine is a halogen, so it tends to form -1 charges. Those perfectly balance each other out. So we say that its formula unit is NaCl. There's 1 sodium for every 1 chloride. Now, in an actual lattice structure, you're going to have ions where you're going to have positive ions and negative ions in this repeating like lattice here. And all of this means is that it's not easy for us to tell whether this is a compound or this one's a compound. But we do know that it's a 1-to-1 ratio. And so that's why you'll see people using a formula unit, like how many units of the sodium chloride there are. In this particular drawing, I drew 6 units. But it's not really easy to tell how you're counting that, because you could count it differently and still come up with 6. Aluminum oxide is going to be a little different. When you have aluminum, it forms a 3+ charge. Oxygen forms a -2 charge. Now, in order for those charges to balance, you would need an additional oxygen. That makes -4. That still doesn't balance out the +3. So if I add another +3, that's +6 now. I'd need to add yet another oxygen to get to -6 to cancel that out. So if I were to draw a lattice for aluminum oxide, I would need to draw the aluminums in a 2-to-3 ratio with the oxygens. And that's going to be a more complicated lattice structure. You don't necessarily have to be able to draw that, but just understand that it's a 2-to-3 ratio. So you will have different numbers of positive to negative ions than you would in the sodium chloride structure. Now, I mentioned polyatomic ions very briefly before. There's a handful of polyatomic ions that you need to memorize. They are sets of nonmetals most of the time where they have covalent bonds between them, but they have an overall charge. So you need to know, let me write it out nicer, nitrate, which is NO3 with a -1 charge. So that means you've got a nitrogen covalently bound to 3 oxygen atoms, and the whole thing has a charge of -1. So it can attach to positive ions and make up your ionic compound because of that negative charge overall. Sulfate has a formula of SO4 with a 2 negative charge overall. Phosphate is PO4 with a -3 charge overall. Hydroxide is OH with a -1 charge. Hydrogen carbonate, which is in baking soda among other things, but it's HCO3 with a -1 charge overall. Carbonate, so just without the hydrogen, is CO3 with a 2 negative charge overall. And then the only positive one on this list is ammonium, which is NH4 with a +1 charge overall. So these are the 7 that you should commit to memory. I like to have my students remember chlorate as well, though it is not required by the IB. It does pop up somewhat frequently. Chlorate is CO3 -1. Just in examples that you might encounter from other sources. So it might be worth your time to remember chlorate. And you can also replace the chlorine with bromine or iodine because of the halogen group. So if you have like a BrO3-, that's bromate. IO3- is iodate. And so those you'll see a little bit more frequently than some of the other polyatomic ions, but definitely know this list on the left. So let's look at this example. It says, what is the charge on the ion formed when the following elements react? Lithium, oxygen, and aluminum. Lithium's in this first group, alkali metal, so it's going to form that +1 charge. Oxygen is all the way over here. It's in group 16, and so because it has 6 valence electrons, it's likely to gain 2 valence electrons to fill up its shell. So oxygen forms -2 charges. Aluminum is here, it's in group 13. Aluminum has 3 valence electrons, so it's likely to lose those 3 and form a 3+ charge. Let's practice naming these ones using their oxidation numbers. Remember, for these transition metals, we can effectively use their charge instead of like an oxidation state. So in this case, for the nickel, it's attached to 2 fluorines. Fluorine has a -1 charge because it's a halogen, and there's 2 of them. So that means the nickel must be a +2 overall to cancel out the -2s. So we have nickel 2 fluoride. And remember, the second one changes to ide. TiO2, oxygen forms a 2 charge. And since there are 2 of them, that's 4 negatives overall. The titanium must be 4 positives then to cancel it out. So this is titanium, Roman numeral 4, oxide, titanium 4 oxide. All right, and then the last one, V2O5. Oxygen has a -2 charge again, so that's -10 total. The vanadiums must add up to +10, which means each one has a +5 overall. So vanadium 5 oxide in this case. So this section links to some of our periodic trends, and we did talk about the ionic charges. Oh, that is a weird looking periodic table. There we go, a little better. So the transition metals will have a variable charge, but otherwise it follows the pattern +1, +2, +3. Group 14 can be + or -4 depending on the context, although it's not very likely to form ions at all. And then group 15 picks up 3 negative, 2 negative, and then 1 negative for the halogens. The noble gases don't tend to form ions at all. So you can use that position to very quickly figure out the charge on an ion. This also links to successive ionization energies. This is an HL topic. So the transition metals, because their electron configurations typically end in 4s and 3d, although sometimes you won't see the 4s. The 4s and the 3d sublevels for those top row transition metals, they're so close in energy that the difference in ionization energies between them is very small. So that makes it easy for it to make different charge ions. Since you only really need to know about that first row transition metals, you only need to worry about the 4s and 3d, although that pattern does repeat for the other rows, so it's like 5s and 4d. So they're very close in energy, which means that their ionization energies are going to be much closer than, say, for a representative element. This section also links to redox reactions, formation of an ionic compound from its elements. So let me choose a simple one like sodium and chlorine gas forming sodium chloride. Elements by themselves have an oxidation state of 0. But then in the compound, the oxidation state for sodium here is +1 and for chlorine is -1. So because we have these oxidation states are changing, it is a redox reaction. The chlorine is being reduced and the sodium is being oxidized. And so anytime you're forming an ionic compound where there's charges from their elements, which have a 0 oxidation state, you will necessarily have a redox reaction. Okay, so how is formal charge used to predict the preferred structure of sulfate? We talked about polyatomic ions. So let's link it to formal charge. When you have something like SO4 with a 2- charge, the sulfur has 6 valence electrons, and so do the oxygens. So that would be 30 valence electrons plus 2 extra for the -2 charge. So it's 32 valence electrons. When I make my compound, I use up 8 electrons in the bonds. So I'm left with 24, and then I'm going to fill in the octets of the outermost elements first. And so that uses up those 24 extra valence electrons. However, we need to check formal charge. Formal charge is the number of normal valence electrons, so 6 in this case, minus the electrons assigned to it, 1 for each of the lone pair electrons and 1 for each bond. So for oxygen, that would be 7, and it would have a -1 overall. Sulfur in this case normally has 6, but right now there's only 4 assigned to it. So that's +2 overall. We can minimize formal charges by changing lone pairs into double bonds, bringing this oxygen down to 0 and this sulfur to just +1. I can do that again and change another lone pair to a double bond, bringing both of these down to 0 and minimizing the formal charges. So we know that the structure of sulfate is going to have 2 double bonds in various places, but that's much more preferred than having the 4 single bonds. Polyatomic ions are also important examples of conjugate bases of common acids. So if you look at something like chlorate, you could have variations on chlorate like HClO2, HClO3, weird, and HClO4. Now, the chlorate part of that, this is chlorate, this is perchlorate, this is chlorite. The more oxygens are there, the more stable the anion is. So when you have ClO2 minus, ClO3 minus, and ClO4 minus, the additional oxygens help to stabilize the ion through the delocalized electrons. So since this is more stable on its own, it's easier for the hydrogen to leave, because it's leaving behind an ion that's very stable. If it's easier for the hydrogen to leave, that makes it a stronger acid, which means it's going to have an increased value of the dissociation constant Ka. And the reverse is true. When you go down, fewer oxygens makes it less stable, which makes it harder for the hydrogen to leave. So it makes it a weaker acid with lower Ka values.